Good morning or good afternoon. My name is Atarod Azizin Amini, Director of the ABC UTC, and very warm welcome to our May 2022 monthly webinar of the ABC UTC. Before we get on with the presentation, there are some important information that we would like to share with you with respect to the conference and also ABC related news that Mary Lou will cover. First of all, the conference, the upcoming conference 2022 is going to be fully in person, no hybrid. We know that everyone is tired of the virtual conferences and they would like to meet in person. So December 7 to 9 of 2022 at Hyatt Regency Hotel in Miami, Florida. The online registration is open. Please take advantage of the early bird registration deadline, which is August 26. We are also delighted to tell you that there are limited travel scholarship that is available, and actually the link where you can apply for this travel scholarship is shown on this slide. The copy of these slides will be posted on our website, so don't worry if you are not able to copy them. The travel scholarship is only for the US engineers, and it's limited. The numbers are available. It includes 4 nights at Hyatt Regency Hotel, registration to attend the 2-day conference, and registration for the pre-conference workshop. And the priority is going to be given to authors presenting at the conference. County bridge professionals are encouraged to apply. Again, these are the travel scholarship for state employees. State employees only in the US. The continuing education. The conference, you will receive a certificate for the number of the hours that you have attended the conference, and you can present that certificate of the interest of the attendance to your professional board to get the continuing education credit. And also, we need to mention that the FIU is official sponsor of the continuing education in Florida and New York. So we are certified to provide a continuing education in the state of Florida and the state of the New York. Call for the award nomination is on. The deadline to submit your application and your nomination is August 22nd. And the link to where you can download all the requirements and all the forms that you need to submit is shown on this slide. Again, the copy of this PDF will be provided at the website. The award categories include Best ABC Project in the following categories: lateral slide, self SPMT, prefabricated bridge element and system, emergency, and international. We do have now international case studies too, so please take a note of that. Also, the award category includes most impactful bridge engineering technology and the ABC person of the year, most influential person contributing to the cause of the ABC. Day before the conference starts, we will have 4 workshops. Each one of them is 4 hours. These are devoted to design of the steel bridges, using the AASHTO LRFD bridge design specification. These are beyond just the ABC. It covers basically the basics, fundamentals of the provisions, the AASHTO code for design of the steel bridge, using AASHTO LRFD, pre-stressed concrete, and then FRP, and then there will be a workshop on the Uhpc. Just to give you an idea, the pre-stressed workshop is going to be taught by basically the practitioners. Dr. Bijan Khalegi is going to be covering. These are some of the topics that you're going to see: basic philosophy of pre-stressed concrete materials, time-dependent, transfer length, camber, flexion shear design, post-tensioning, seismic designs, and basically design of the splice girder bridges and complete pre-stressed concrete bridge design example. So there will be a complete design example that the Bijan will be covering. The workshop also includes some of the biggest names that you see in the pre-stressed concrete world. William Neckes will be discussing the basically the best fabrication schedule while optimizing the fabrication costs and ABC considerations. Greg Freeby will be discussing basically the segmental bridge design and construction, okay? A recommendation for the segmental bridge design, fabrication, and construction while optimizing the project cost. Also, there will be a section, 20 minutes, summarizing all the available tools that you need, basically to all the resources that will help you to design pre-stressed concrete bridges in accordance with AASHTO and RFD. We are getting overwhelming really responses to this conference. We anticipate very large attendees. So, and there is opportunities for exhibit. We have received many applications, have already signed up for exhibit. Please don't miss this opportunity to exhibit at the conference. And finally, if you have enjoyed all these webinars that we've had, all these activities, we hope that you will consider very seriously to attend and support the ABC UTC.
Our presentation today features South Carolina's experimentation with ABC technology in its S-770 bridge over Hanging Rock Creek in Lancaster County. We're pleased to welcome our presenter, Terry Koon, Structural Design Support Engineer with the South Carolina Department of Transportation. We'd like to also introduce our Q&A session moderators, Paul Lyles, formerly Georgia State Bridge Engineer, and Jugesh Kapoor with WSP USA and formerly State Bridge Engineer at WashDOT. We'll now begin our featured presentation. Terry?
Thank you, Mary Lou, and good morning or good afternoon to everyone, as the case may be. I'm going to do my presentation on the experimentation with ABC technology in South Carolina. Specifically, I'm going to talk about the secondary 770 bridge over Hanging Rock Creek. Before I start in talking about the bridge specifically, I want to talk a little bit about where we are with ABC technology in South Carolina and maybe some of the plans for the future. We have, as I started this presentation, I didn't realize what all was ABC type bridge elements. And I looked on the ABC UTC website, and there was a lot of them that we have already done, and I did not realize they were considered ABC type technology. So I'm going to kind of mention some of those and talk about some of them we've done or do routinely or have done in the past. For the deck elements, we have done FRP bridge deck panels. That's been used on one project in the northwestern part of our state in Spartanburg County. Deck beam elements, we have currently an adjacent decked AASHTO Type 3 beam that's currently under construction in Newberry County. That's our first one of those. We have adjacent inverted T-beams, which we've used one with what we call adjacent beams, and then we've used two other with a spread pattern in order to reduce the number of girder lines and also provide a little bit more space between the beams for visual inspection. We've used adjacent box beams, although they've been kind of limited thus far, but we are considering we're currently developing policy and planning on developing standard drawings so that we can kind of promote the use of those more than we are now. Adjacent slab beams, or the Hollow-Core or cord slabs, as you'll probably hear me call them during the presentation. So you just have to bear with me if I say cord slabs or Hollow-Core. That is the same superstructure type, but we call them cord slabs here. But I was trying to keep with what I think is the proper name of Hollow-Core. But anyway, those we use a lot of cord slabs throughout the state. But they are restricted to non-national highway system routes with traffic counts of less than 3,000 vehicles per day. Also, for full width beam elements, we've used the precast segmental type construction on I-526 Wando River in Charleston. I think that bridge has been around for about 40 years now. Also, for pier elements, we have, as far as precast columns, we use a number of pre-stressed pile vents within the state. But we do use cast in place caps with those. We have not really developed precast caps to a large extent. They are common on the coastal plain of our state, where we have sands and silts and clays and don't have rock near the surface. Steel columns, so we use steel piles with cast in place caps. Those are typical substructures for the indents. Almost basically all of our substructures that we build have the steel pile vents, unless the soil conditions don't warrant something else. Micropiles, we don't use them commonly, but we have used them, but we use them usually where there's confined overhead space and we can't get a regular pile driven driven as normal. Lightweight fill, we have used that in a time or two in order to reduce the pressure on the wall, on abutment walls on bridges. For abutments and wall elements, we have used the precast sheet piling on one project where we used it as the indent, and the bridge's weight is bearing on that. For MSE walls, we do not typically put the bridge end bearing on the wall itself, but we do use pile bents that are placed deep foundations placed behind the walls, and the MSE walls go in front of the abutments, and that's mainly used on overpasses such as railroads and highway overpasses. Modular block walls, typically not used at bridge abutments. We've used a couple of them in the past, and we've had some trouble with the filled material spilling out from behind them, so we use them for maybe regular roadway walls, but not as much for bridge abutments. As far as bridge buried structures, we have three-sided precast culverts. We do use those, although they're not commonly used. The buried precast box culverts are very commonly used in South Carolina for culvert options. Also with the miscellaneous elements, we have precast approach slabs. We have used one experimental project with precast approach slabs. Steel diaphragms are commonly used, especially for I-beam construction, although we do prohibit them where the low chord of the bridge is lower than 20 feet mean sea level. In other words, near the coast, we would not use them if it's a low-level bridge. But on higher-level bridges where they get above that 20 feet, then they may be used in that situation. Closure joints and connections, cast in place reinforced closure joints. Actually, we have the decked astro girder that I mentioned earlier. That is using latex modified concrete as the closure. In that case, and that one's, as I mentioned, is currently under construction. Uhpc closure joints, we're going to talk about that on this project. When I get to talk about the specifics of this project, we used Uhpc. Grouted key closure joints are typically used on hollow-core bridges, and we do normally use grout. In this example I'm about to talk about, we did use Uhpc in those shear keys. Post-tension ducts, not really commonly used, but we do have a few in the state, including the one that I mentioned about the segmental bridge in Charleston over the Wando River. For overlays, we have asphalt overlays with membranes. That is our typical operating procedure for what we use on core slabs, at least the ones that are designed within pre-construction. Maintenance does use the ones without the membranes, but on the ones they have built, they would eliminate the membranes, but we have kept the membranes on ours. Latex modified overlay, that's primarily used on widening projects where we use the overlay on the existing portion of the bridge, but we do use it on rehabilitation projects as well when we're trying to rehabilitate the decks. And talking about some of the challenges in implementing ABC construction techniques in South Carolina, historically, there have not been a lot of attempts to accelerate construction, as I guess what I would consider like ABC type construction. We have in the past kind of maintained the stance that we would maintain traffic if it was critical to keep the road, keep the limit public inconvenience to a minimum. We are kind of shifting a little bit where we are starting to close more routes and replace them on alignment, save time and money. And we also our state is starting to grow in population and development, and we find a lot of bridges that are in more urban environments now. So I think we will have to look at implementing ABC type construction techniques in the future in order to accelerate the construction even more than what we have now. Seismic potential is another concern of ours. South Carolina has the highest seismic risk on the east coast of the U.S. We need to have connections developed for segmental construction that can prove that they can resist higher seismic forces in a higher seismic zone, earthquake zones. Foundations. We typically use cast-in-place construction, and as I mentioned, we do use pile bents with the cast-in-place caps, but a lot of our interior bents are generally drill shafts, what we call them drill shafts on cast-in-place bents. So that's kind of our typical foundations that we use. A lot of that is due to the soil types we have. In the northwestern half of the state, we do have rock relatively close to the surface, although we can drop piles and occasions there. But but in the lower part of the state, we have a lot of coastal plain, and it's got silt, sands, and clays that are sometimes very difficult to, that would be kind of difficult to install a segmental foundation on. Also, we have the seismic concerns, you know, due to liquefaction, that also kind of create some limitations for us on using segment, or excuse me, ABC type foundations on our bridges. And to continue on, currently there are no structural design or construction policies promoting accelerated bridge construction per se. We do have incentive, disincentive bidding methods such as A+B and A+B+C, but usually the time estimates are considered based on the typical construction methods that we use, and not on trying to accelerate the project. We have not been able to successfully so far develop language and design build proposals to encourage contractors to use ABC techniques, so it's kind of their call as to what they do. We talked about it on a recent interstate corridor improvement that we're starting construction on, but we couldn't figure out a way to how to write it such that we would encourage the contractors to try new methods which would help accelerate construction. Our current organizational structure is a little bit different from most of the state DOTs. We have regional production groups. We do not have a central bridge design office per se, with a central state bridge engineer or a state bridge design engineer. My office, for example, is in the structural design support office. I'm responsible for quality assurance and quality control. The regional production groups, as the word says, they are about production and trying to produce the plans. They do that with some in-house staff as well as consultants, which do a lot of our work. So trying to communicate, instead of having that central structures figure that can kind of supervise you know, the engineers and try to keep them using new techniques and technology. There's we have to do a lot of communication and coordinating to use new technology in South Carolina. And so what's next for ABC in South Carolina? Well, our bridge design manual is currently being rewritten. It will be called the Structures Design Manual. Also, a project has been planned to add and revise standard drawings for cast in place, as well as pre-stressed concrete bridge elements. We've already underway with that project, and as one of the chapters will be devoted to accelerated bridge construction. Haven't seen a draft of that yet, but I think it's going to be more of I guess a philosophical or methodology approach, and it might not get too specific on details at this time, but we'll see as we go along with the development of that chapter. We also plan to incorporate a discussion on Uhpc in the Structures Design Manual. It will probably be in a concrete chapter, and in order to kind of promote the use of Uhpc when it would be helpful to do so. Box beams will be added to the manual, as well as our standard drawings to encourage their use and standardize their use. And we're also planning to do some off-the-shelf type standard drawings. Our current drawings are all considered modifiable drawings that you take and have to modify for each particular project. These will be more or less where you can pull them literally, I guess, off the shelf more or less, and compile a set of bridge plans, or at least the superstructure portions in relatively quick period of time, using charts and tables to direct the contractor on what he needs to do to build the bridge. And those are planned for our box beams and hollow cores. And the intent of that is really more so for our low volume bridge program, where there's lower risk. The higher volume roadways, I would anticipate we would still use mainly custom drawn design plans. And with that, I'm going to start talking about the S-770 bridge over Hanging Rock Creek. Again, it's in Lancaster County, South Carolina. In Pennsylvania, I think it's pronounced Lancaster, but we pronounce it Lancaster down here. As you can see, this is the existing bridge, and it's, as you can notice, is definitely in need of replacement or some work on it. Ironically, as I looked at the photos on this, this was actually an ABC project years ago. These were standard bridge types that were built by maintenance forces and contractors back in the 1950s and 60s. As you can see, there is timber pile caps and precast piles supporting pre-maintenance slabs. The rail was attached at the end to provide the barrier protection. These were a very economic and quick to build type of structure, and there's a number of them in the state that we're currently in the process of replacing. I also, before I get started and talking about the project itself, I was going to talk a little bit about who was involved in the project. We started out by receiving a special grant from Federal Highway Administration through the Innovative Bridge Research and Deployment Program, or IBRD. That program is no longer active, but that's where the funding came from for just the portion of the technology testing. So basically the research and the I guess the additional amount of materials and construction efforts that were required to implement the NXDs that we used on this project, and also the other modified solid slabs. We had a deployment of the NXD beam. The NXD beam was developed for South Carolina purposes by Clemson University through a research project. Also, they developed Uhpc pre-qualification special provisions, as well as some non-proprietary mix designs through another research project. And then the bridge itself was designed by the Midlands Regional Production Group in-house. Fabrication of the pre-stressed superstructure was by Techna Corporation. The construction was by Dellinger Incorporated. UHP supplier, Lafarge Wholesome Ductile. Construction engineering and inspection was by District 4 Lancaster Construction Office, and testing and monitoring program was by Clemson University with the assistance of Dellinger and SEDOT Lancaster Maintenance Office. And to give you a little idea of where the project is located, of course, South Carolina is on the southeastern side of the United States along the Atlantic Ocean. And this is South Carolina, and for those of you not familiar with the geography of our state, and Lancaster County is located right here in the northern portion of the state, bordering North Carolina. And the project itself is located to the extreme south of the county, near Kershaw County. And zooming in a little bit more, here's the town of Kershaw, which coincidentally is in Lancaster County, even though Kershaw County is just below it. The site is located about 2 miles south of Kershaw County. And now we'll start talking about details of the bridge. You'll see the bridge planning profile here, and I apologize in advance. I know this screen is kind of small to see, but I'll try to talk through what kind of the highlights of what we're looking at. The bridge had actually 3 distinct superstructure types. It was kind of more or less an experimental type bridge. It had going from left to right across the screen, or north to south along the bridge. It had a 40-foot modified NXD beam. It had 2 traditional 70-foot cord slab spans that are common to what we commonly used here. And then we had a 40-foot solid slab with modified shear key, which is basically a cord slab without any cores in it. The bridge itself is 200 feet long with 20-foot approach slabs on either end. The overall bridge width is 42 feet. And just to talk about the substructures again, this is a very typical substructure in South Carolina, where we have the steel pile indents with cast in place caps with the multi-column drill shafts supporting cast in place caps. And like I said, that is a very typical substructure type that we use in South Carolina. As I mentioned, we used a modified NXD beam, and these are 3 of the sections of the NXD, at least at the time that were developed. It's a F, a E, and a D beam. The F and the E require partial cast in place deck overlays, whereas the D beam does not. It can actually be a riding surface, I guess, if you want to use it as such. And again, through Clemson's research, this is the section that the D is what they picked up on and want to try to develop as the new section of ABC type section we were looking for. So here's some of the objectives that we tasked Clemson with coming up with. We wanted a compositely acting superstructure that's more durable than our cord slab details. We feel that the cord slab details, because they're not really a truly composite bridge, that they will not last as much. They'll deflect differently, and we don't consider them as durable as some of our cast in place options. We also want a structure that could be used on routes exceeding 3,000 vehicles a day, which is the current limit on cord slabs and solid slabs because of our concerns about the durability. Comparable to cord slabs and flat slabs, so basically short to moderate spans, the range that we would be looking for using these types of spans, and installed in an accelerated time frame versus the cast in place superstructures such as our flat slabs, which are very durable, but of course require a little bit longer construction time. And here are the two sections of modified NextDs that we used for this project. And I think they're more or less modified based on trying to fit them up to the size that we would need to meet the geometry of our roadways. The exterior span on the left is about 7 feet across, and it's 1 foot 9 inches deep. The interior span on the right is approximately 6 feet across, and again 21 inches deep. And they're pre-stressed. Here's a section, just the first unit that was cast on the fabricator's yard. You can see the U-bars protruding from the cords from this, the NextD in this case. That would be used to make the connection between the units. Here's the next typical exterior units. You can see the bars coming out of the cord or the NextD that are serving as the bottom bars of the parapet. This was built pre-mash, so this is a jersey barrier. If we used one nowadays, we would have to incorporate our new mash barrier, which is more vertical, more of a vertical or rectangular shaped wall. So we would have to redo a little bit on the barrier in that case. And here's a typical section through the NextD beam. As you can see, it's composed of 4 interior units and 2 exterior units with 5 shear keys and closure pores, and those are filled with Uhpc. Again, the overall bridge width was 42 feet, and the roadway width was approximately 40 feet. Here's the closure pore detail. As you can see, the 2 U-bars protruding out of the NextD beams with longitudinal bars threaded through the U-shaped bars. The key is approximately 8 inches wide at the minimum, and I think including the shear key, it's about 10. Including the shear key into the NextDs is about 10 inches wide, and full depth, which is 8 inches in this case. And that was, again, it was filled with Uhpc. Here's the closure pore set up here. The bars, the horizontal bars are missing in this photo. They need to be threaded through there, and the formwork's not yet set. But anyway, that gives you a good indication of what the closure pore kind of looks like pre Uhpc. Okay, going on to the 70-foot hollow-core slabs. Here's it was 12 interior units and 2 exterior units. Again, 42-foot width. We have these smaller shear keys that we typically use here, and normally they're filled with grout, but we decided to go with Uhpc in this case. We do use tie rods to secure our slab units together. That was at the request of maintenance in order they could easier disassemble the bridge if they had to and reassemble it. So we don't use the pre-stressed strands as I think I've seen in some details. Also, you might notice that we have an asphalt overlay. And just to let you know, this asphalt overlay does vary in thickness, especially out on the outside edge. We try to hold 2 inches at the bare minimum. And, you know, at the bearings, it's thicker, depending on the vertical curve ordinate. And, you know, in order to provide a better rideability condition. So we have to vary the asphalt overlay to account for the camber and the different adjustments in the grades. So here's an typical interior unit detail for the hollow-core slab. The 70-footer is 3 foot across and 2 foot deep, and also 2 12-inch voids. You'll notice later on, and also if you remember in the NextD beams, those are 1 foot 9, and those are shorter spans, so we didn't need the entire 2 foot. We used 2 foot depths for 60s and 70-foot hollow cores. Here's a couple of interior units that have been cast on and sitting on the fabricator's yard. This gives you a good picture of the shear key layout for the cord slabs. And here's a typical exterior section with the rebar protruding out of the top that help form the barrier steel. And then the last span was a 40-foot solid slab with modified shear keys. Again, there were 12 interior units, 2 exterior units. They're still 3 foot across. Again, tie rods were used. Larger shear key was used. So since they were only 40 feet in length, we decided to take the voids out and not reduce the load in order to accommodate for the larger shear keys. Again, the asphalt overlay is used, and again, as I mentioned, tie rods. Okay, here's the shear key detail for the modified shear key that we came up with. Of course, it's a good bit larger in size and a good bit deeper than the shear key that we typically use for our cord slabs. And as I mentioned, although you can't see it here, the tie rod goes across through here, and it's in the conduit, and it has a coupler in between that I'll show in just a few minutes. Again, here's a typical interior unit. It's 3 foot across, and as I mentioned earlier, it's 1 foot 9 deep. You can see the conduit protruding out a little bit from the solid slab in order to make a couple connection between the two units. To keep the tie rod, form a watertight seal so that the UHPC cannot leak into the cavity for the tie rod. Here's a cast unit sitting on the fabricator's yard. Again, you can see the larger shear key. This is the interior unit. Here's the exterior unit. Again, you can see the large shear key, and you can see the rebars sticking out that would be used for the barriers. Okay, here's the solid slab in place, and I'll point out the access pockets, which I got a few slides showing those and a little bit closer up. They were spaced approximately 10 feet across along the length of the span, and again, those were used to couple the two conduits together in order to keep the UHPC from leaking into the conduits where the tie rods are located at. Again, here's a side view of the solid slab that's showing the access pocket up here that's been formed. And also you can see the conduit with the tie rod would come through the slab. And you may not be able to see this too well because it's kind of a dark picture and looking down into the shear key, but it's a rubber coupler was used, and it's a band clamps on each side. And again, South Carolina, the tie rods have to be tightened fully, even on a normal cord slab. They have to be tightened fully for the placement of UHPC in this case, or grout in our typical details. In order to make sure everything's good and tight before we pour it all, before we pour the shear keys, because after you pour the shear keys, you can't tighten it up anymore. In South Carolina, the tie rods are used in hollow-core slabs and solid slabs to allow for easier maintenance, as I mentioned before. And the conduits are not filled with grout; they're left open so that, again, it's easier to remove the tie rods. And here's the casting bed for the modified NextD. As you can see, the strands are fully tensioned and the mile steel is in place, and they're about to pour the concrete into the forms. And here's a few views of them as they're pouring along the length of the bed and placing the concrete. And I believe this was 6,500 psi concrete that was placed in this particular unit. And here they are setting the modified NextDs. Again, they're relatively light spans, so they were, I think, relatively easy to put in place. Here's the end of one where you can see the bearing detail much more clearly. What we normally use is we have embedded on the stems. We had embedded sole plates, metal sole plates, and they were welded to our bearing plates. Underneath, there's a 3/4 inch non-laminated bearing plain elastomeric bearing pad, and then they were tied to the bent caps using anchor bolts. And now we're going to start with some of the placing of the UHPC in the joints after the bridge has been in place. You can see the contractor was allowed to use the non-proprietary mixes that Clemson designed, but we did not prohibit him from using a proprietary mix, and he's chose to use the ductile in this particular situation. And you can see the two mixers that they had on site. They have the bag of the dry mix, and they drop it in, cut open the bag and drop it into the hoppers and start mixing. Here are the microfibers that are being mixed into the UHPC mix. Also, and notice these are gold colored, but this is not gold microfibers. They are actually steel coated with brass to keep them from corroding. So they're expensive, but they're not that expensive. Here we go with starting the UHPC pour. This is an enclosure pour of the NextD beams. As you can see, they started out using a trough to kind of direct it into the shear closure pour without spreading out everywhere. Here's some progress of the closure pour. You may can see this and might not notice, but anyway, after we got about this point, we realized that the Horizontal bars that were supposed to be threaded through the U-bars were not in place. So we had a brief discussion on the site, and it was determined that we'd go ahead without the bars, as it would be very difficult to stop at that point and remove the Uhbc and start over again. Also, this was on the outside on the shoulder of the bridge, so we didn't feel it would be a big deal. We don't really think those bars that would be threaded through would provide that much more strength anyway. And also, it gave another variable in the test case for Clemson to test when they were doing their load testing. Here's some of the methods that they used to make sure the Uhbc got to the top of the forms. They used plywood forms and nailed them down. This was on approximately 0.3% grade, so it wasn't level across the length of the bridge. So they had decided to come up with this 5-gallon bucket with a hole punched through it and also through the formwork, and they would build up a pressure head by putting Uhbc in the bucket, and that would help kind of make the Uhbc flow into any cavities that were left below the formwork. And here's a couple of my co-workers. They were given some hammers and told that they were going to have fun, but actually they're actually helping to place the Uhbc. The hammering of the vibration of the hammers help the Uhbc flow, and that you just start hammering down the length of the formwork, and that helps the Uhbc further flow into the cavities beneath the formwork. And so since we did not have the U-bars, or excuse me, the longitudinal bars placed in the next D closure pores, we had to stop working on that one for the day, and they moved along to the first 70-foot cord slab. Here you can see this much smaller shear key that they had to squeeze the Uhbc inside. And here it is in place. So now I'm going to talk about some lessons learned and some observations that we made during the project. At that time, especially, this was 2016, 2017, Uhbc was presently expensive. It was a very expensive material. There was a lot of non-proprietary options out there. And we found out that Uhbc moves very slowly, but it does behave like water, and it seeks its own level. So it can be challenging to install on a vertical grade. And one critical thing is you've got to provide watertight seals for UHP installation. One thing that I came across the other day when talking to one of our resident construction engineers is during the project, when they removed that formwork, some of the Uhbc had settled down. It was like a 1/4 inch below the deck surface, and that wasn't supposed to happen. So we think maybe some of the seals were not as watertight as we thought they are, and it lost some of the material, and thus it was settled. So anyway, as I understood, the contractor looked for a grout mix that he could come up with to fill it back up to the top of the decks, but in essence, it didn't really make a difference in this case because we're using asphalt overlays anyway. So we could I guess basically cover that up, and it wouldn't be a big deal. Again, as I mentioned, ensure that the horizontal bars installed in closure pores before the Uhbc is placed. There's not much steel on the job site when you're using these segmental units. Actually, outside the barrier, this is the only other steel that they had in the superstructure. So I guess there was a miscommunication in who was going to deliver the bars. So they got left out to begin with. You got to take safety precautions when handling Uhbc mix. As far as the material, the dry mix itself, you don't want to breathe that material. It was very harmful to your lungs. And also because of the metal filings, you've got to be very cautious about handling it. It can cut your hands up pretty severely, so you got to take some precautions when using the mix. Also, installation of Uhbc is easier, certainly in the larger closure pores that we had versus the typical shear keys that we have in the Hollow-Core slabs. You need to develop special provisions for installation. That was something that we missed when we let the project. We had Clemson develop some pre-qualification specifications because at the time we were thinking that we might use the non-proprietary mixes, and we just wanted to make sure that the mix design the contractor came up with would perform to the criteria that we needed it to. But we thought we could use the standard specs and use normal concrete placement and handling specs that we have in the standard specs. But as we found out, that was not necessarily the best plan, because the first attempt at the pour was on a very cold day in South Carolina, with temperature barely got above freezing, and that's very rare that happens in South Carolina, even in the winter time. But in this case, it was even in early March, so that even caused, or middle March, so that was even more of an unusual weather phenomenon, that it was so cold. So they had to wait about another week before they actually attempted to pour when the weather was a little bit warmer. I'll talk now about the research reports that were developed. It was 3 total in this. As you might notice, the first 2 have the same report numbers, but they were kind of developed in unison together. One kind of complements the other one, so we gave them the same report number. The precast alternate for flat slabs, that's where the research was done to develop this alternate section, ABC section, that we could use as an alternate to the flat slab, cast in place flat slabs. That report was completed in October 2013. The second report, development of high strength, high performance grout, concrete grout mixtures for applications of shear keys and precast bridges, again by Clemson University, completed in August 2014. And the third report was actually the report produced because of the IBRD funding, and that was performance evaluation of SCDOT next D beam bridge. That was all the testing of during and after construction, and again that was by Clemson University. The report was completed in September 2019. And as you see, all 3 of those are the web links to all those reports. They're on our SCDOT Office of Materials and Research website. And talk a little bit about report 1, some of the objectives. Again, I've mentioned some of this earlier, but to develop a short to medium span superstructure type that has durability comparable to the cast in place flat slab, but faster construction such as the hollow-core slab without the shortcomings of the hollow-core slab. We also want to eliminate or minimize the longitudinal and transverse cracking of wearing surfaces that we experience using asphalt overlays in the core slabs. Again, they don't have composite behavior because the tie rods can't be tightened enough to cause complete composite behavior, so it causes reflective cracking through the asphalt overlay. We also want a superstructure type that had a lower initial price and lower maintenance costs overall. We wanted a shorter construction time than the cast in place flat slab would give us. Wanted a longer service life than hollow cores, because we believe that those are not as durable because of the non-composite action. And also, like I say, we restrict those to lower volume routes. Determine appropriate distribution factors of the new superstructure and compare them to what's in AASHTO to see if we're using the proper distribution factors for our designs. Basically, report number 2 achieves 2 things. One, it has developed some non-proprietary mixed designs that we could possibly use on projects. The second feature was the specifications for the pre-qualification of UHPC mix for DOT use. And the research conclusions and recommendations for report 3 is the details of the modified next D beams performed well during the testing, and no modifications were anticipated being needed. No visible signs of cracking at the closure pores or shear keys. Recommended use of type K, which is the precast I-beams and cast in place decks for the distribution factor for moment, and that's in AASHTO LRFD. The longer spans should be evaluated possibly up to 60 feet, because the shorter spans in South Carolina, we seem to have a trend growing that because of hydraulic reasons, we're having to use longer and longer spans, and there's not many opportunities to use a span that's only 40 feet long. Modified next D beams should be evaluated for traffic counts exceeding 3,000 vehicles a day to test the technology to its fullest. UHPC is recommended for closure pores and shear keys. So now I'm going to talk a little bit about the overall project cost. The total project cost was right at $3 million. The total bridge cost was right at $1.5 million, or $157 per square foot. Cost of UHPC for approximately 15.5 cubic yards was $11,000 per cubic yard. The modified next D worked out to $700 per linear foot. I'm sure we paid a lot for that formwork, that specialized formwork that they had to create for that. The 70-foot hollow-core slab units ran about $150 a foot, and the 40-foot solid slab units ran $150 a foot. So you can kind of see a comparison in superstructure costs there, 150 versus 700. But and comparing, just to give that you a comparison to that, the 2016 average bridge cost was right at $196 a square foot. So in this case, it was a little bit under the average cost per square foot for bridges in that year. Give you a construction timeline. The project was let to construction in February 2016. The project the construction began on May 2016. The substructure construction began around November 2016. It was completed prior to March 2017. I don't know the exact date, but it's approximately 4 months as to when that was completed. Hollow core units, solid slab units, and modified NextDs were placed the first week of March 2017. Uhpc was placed on March 20th, 2017. Again, we tried about a week earlier, but that didn't work out because of the weather. Asphalt roadway approaches and bridge asphalt overlays were completed by June 2017. The bridge was open to traffic July 2017. So the bridge construction time was approximately 5 to 6 months. For that, I guess, as we mentioned, was substructure. So that left about 1 to 2 months for superstructure. So that was gave us a pretty fast speed on our bridge construction. The total project construction time was 1 year and 3 months. And that concludes my presentation, and I guess I'll take questions now.
All right. Thank you, Terry, for a very detailed and very informative presentation. So at this point, we're going to turn it to Paul, Jugish, and Jamal to moderate the question and answer period. Paul, it's all yours.
Yeah, thank you, Torrid and Terry. A very interesting presentation, and we do have a bunch of questions that came in during the session. We'll start off with some questions that came in beforehand. And the first one I have is, beside performance comparisons between the superstructure types, were cost and design life also considered in this project?
Well, certainly our goal was to achieve a greater service life using the Uhpc and the NextD beam. It was to test out technology. I guess as far as the upfront cost, we knew that was probably going to be a little bit more expensive. But I guess basically the project was really about testing performance, but I think we got some side benefits of putting a little bit more durable bridge out there than we may have used in the past.
Okay, we had a question that was beforehand. It says, was an overlay necessary? If not, how is the roadway crown achieved? You used the overlay to do the crown, I think.
Right. Yes, in this case, we built the bridge, I guess, flat or level, and then used the overlay to form the crown. This could be used. I think the deck certainly structural wise is strong enough to use as the direct as the riding surface. You may need to put a little bit more depth to it in order if you had a groove surface finish or something like that. You would also have to probably have the closure pour in the center of the bridge on the crown point if you use the crown, and I guess you'd have to slope the cap. But certainly you didn't need the asphalt overlay. A lot of the reasons that we used it was because of the fact that we used the hollow core slabs and we needed the overlay for those.
Okay, another part of that question was, what are the maximum span lengths you can use with these two types of beams?
Well, the Clemson report, they came back with about 60 feet potentially. This was certainly a custom design for this particular project. So design wise, we're not sure at this point, but Clemson anticipated maybe up to 60 feet, somewhere along there.
Okay. Then a question that came in beforehand was high strength epoxy grout considered as an alternative to the Uhbc that y'all used? And if not, why?
No, it wasn't. Clemson, of course, developed the NextD as well as the material that went into it, and they decided that Uhbc was the product to use. Also consider at this time was 2016, and I think their research started back in 2009. So it may have been some of it was technology, what the technology was at the time. I think you could use other mixes potentially, but we went with Uhbc because that's what we were recommended to do.
Okay. I got two questions. One came in beforehand, one during the presentation, and this is on your next beam. It says, why was the South Carolina approved cross-section different from the standard next beam? And hang on, let me get one other one here. And is what is the narrower width of the next beam? 6, 1, and 7 is what you used on this bridge. Was it for shipping and handling reasons, or was there something else why that was used?
No, well, yes, the modifications were done basically. I think both the answers to both questions basically because of geometry of roadways. Of our roadways, we wanted to use something that would fit our roadways. In this particular case, we was using other superstructure types, so we had to kind of work with what we had. The cord slabs are 3 foot across, so we had to work in increments end up with increments of 3 foot in order to achieve a roadway width. So the cord slabs had to be adjusted across width-wise to achieve the same roadway width. So it worked out that the interior units we went with a little bit smaller span, but it had nothing to do with handling. It was more about just trying to work out a section that we could effectively match the roadway width of the cord slabs.
Okay, here's one that came in beforehand, and it's a bunch of things, and we'll try and work through them. It says, can you discuss joint installations, bearings, section camber, bridge to roadway transitions, and connections to parapet walls? I'll try and help you a little bit. You discussed you discussed your joint installations a whole bunch. I don't know if you want to add anything to that.
I don't know what else to add on that one. I think if there's more detail wanted, I'd certainly be happy to answer more questions.
How about bearings? What did you use for bearings?
Again, we used on the stems, we had sole plates, metal sole plates embedded, and we welded those to bearing plates, and it's sitting on top of a plain elastomeric bearing pad.
Okay. And on your flats, your hollow-core slabs, would you use a strip pad of neoprene or something?
The hollow-core slabs, again, is just a thin unlaminated pad. I forget basically they're a little bit shorter than the panel widths.
Okay.
I think like 2'6", I believe.
And then there was a question about section camber. I think you probably took care of that with maybe just with the overlay.
Yes, yeah. As far as working dealing with the camber on the bridge, yes, the overlay was adjusted. The details I showed the 2 inches at the outside. That's a minimum. We usually have to work through the camber by putting a little bit more asphalt over the bearing areas so that when you get out to the midspan and the maximum camber, you've got 2 inches, no less than 2 inch overlays.
Okay, and then you had the part of this question about the bridge to roadway transitions and connections to your parapet walls. I'm thinking there maybe the guardrail. That's probably a special thing unique to South Carolina, and just. Yeah.
Again, yeah. To make the connection of the guardrail, we take the Jersey barrier, and right at the end, I'm not sure if this is what they're asking, but we take the Jersey barrier and we would form a vertical wall by the time you get to the end of it, so the guardrail can easily fit onto the end of the barrier without being kind of not level and all. So yes, and I guess as far as is that the approach?
That's fine.
Yep.
You did say that this bridge is Jersey barrier, but you're now into a mesh configuration, and it's going to be a little different. That'll be fine. We had a bunch of questions that came in regarding the beams and the joints and whatever, but let's see if we can get some of those. These are new questions. What is the special tie rod size, spacing, and tension force in the tie rods?
1 1/4. I don't remember the spacing, necessarily spacing off the top of my head. It depends on the length of the span, of course, but some of the smaller ones may have 1 tie rod in the center, and then some of the larger ones I think may have 2 or 3 tie rods.
Okay. Yeah, that's fine. What kind of connection was used between the precast girder superstructure and the substructure to resist your seismic forces?
Okay, well, for starters, this particular project was at a category A, which is our lowest seismic zone. So in that case, we only require seismic detailing, but we use the anchor bolts on the bearing plates. We had anchor bolts sticking up through the bearing plates, and they were tied down with nuts. That was on each stem of the next Ds. For the cord slabs and the solid slabs, what we do there is on the fixed end, we'll fill it with grout. There's a rod that protrudes out of the cap, and we backfill it with grout. On the expansion end, we will fill it with a expandable material, and then we'll stop below the top of the deck. We'll fill the rest with grout.
Okay. Let's look at some of your shear keys and things. And the question came in about, was there any special prep used along the faces of the shear keys in the project?
As far as like adding some kind of I guess something to the sides, like a waterproofing or something like that.
Well, that, or sometimes they go along and they sandblast them to roughen them up.
Right.
You get a better bond or anything like that? Was anything specified?
To my knowledge, we do not require anything to be done to those shear keys. They're basically like they are. Of course, the contractor, I guess, has to get any trash and debris out of them before he pours the grout. Yeah.
Okay. There's a couple questions that came in regarding the flow challenges, and it said, did you have flow challenges with Uhbc into the smaller pockets for the slab options?
Yeah, it was certainly slower to get it in there, and of course you saw the trough in the detail that they used to try to keep it from pouring out everywhere on the deck while they were trying to force it in. But they were able to do it. But as obviously the larger openings are much easier to place the mix, but because it doesn't have any coarse aggregate or large aggregate, it doesn't really make, I don't think it makes a big deal in order to get them into that smaller key.
Okay, and then on the same token, it says, it appears that placing formwork under the joints between the girders could be challenging. How was this done?
I can tell you from what I saw, and I guess it would certainly be challenging near the vents. And I think I had it in one of the photos earlier. We had they had a piece of plywood across the front, and I think I saw one underneath. It was right there under the vent, because the stems you don't have, but I guess about a foot or a little over a foot of room to work with. But out in the span on the next D's, what they did, I think they used plywood underneath, and I guess they attached it with some kind of concrete anchors to the underneath side of the deck, and then they used expandable foam, I think, to try to more or less form the watertight or waterproof portion of it.
Okay. Here's one that came in during your presentation. It says, because this bridge is experimental, are these spans instrumented permanently? And can we see a comparative long-term behavior in the cord slabs versus the next beams and deterioration progress?
Well, the bridge hasn't been in place too long, and it was according to the IBRD, we were only required to test it for 2 years, so we don't have, other than normal inspection reports, we don't have a lot of data, and I don't have the inspection reports in front of me. But as far as I know, it's holding up good. It did hold up good through the testing period, which I think lasted about maybe a year or two after the construction occurred.
Okay, that's fine. There was a question that came in about what was the strength of the Uhpc mix that you used on these pockets?
It was 28-day strength was 21,000 psi.
Okay. And then there's a question that came in right as we started, did the next D-beams exhibit cracking in the underside in the beam to flange corners at all?
We didn't observe any, but again, it was a fairly short span, so I don't think there would be a lot of stresses on the next Ds in that case.
Okay. There's a couple questions that came in. Let's see if we can get them. It says, how is the work on the fib beams? They weren't on this bridge, but for South Carolina coming along. And when can we expect the South Carolina standards for fib beams for their design and construction and implementation in South Carolina?
Okay, so that's somebody that works on bridges in South Carolina, apparently.
Probably.
Okay. Yes, the fibs are being used routinely in South Carolina now. We've adopted them. We don't have them officially in drawings and details yet. As I mentioned earlier in the presentation, we're trying to get a contract up to have a consultant work on drawings and details, and the fibs are definitely on the list of items that we want to develop standards for. So we are allowing them to be used. They started in design build and they moved to design bid build. So they're pretty routinely used in South Carolina right now.
Okay. And along the same line, it seems like the Hanging Rock Creek Bridge is the only bridge that is tried with the next D beams. Are there plans to go with next beams or any other or any other of the beams? If so, are there plans to create standard drawings and designs for these beams?
Well, that was the plan when we started. I guess quite honestly, we have not used one since then. As I think I kind of alluded to in my presentation, our hydraulic designs are requiring us further and further setbacks off the creek banks. We now at a 10-foot setback, which is what we're supposed to have from the creek bank to the piers or the toes of fill. And so that creates a challenge in getting across streams with the next D beams, because we use a lot of 70-foot cord slabs now, and which again is limited to low volume. So I think we might not be looking at as hard as those as we would be the box beams going forward, to see if we could use those at higher volumes, maybe with a reinforced concrete deck. But we're not there yet. We're still waiting for that contract to begin, but that's kind of my thought process right now. They certainly could be used. It's a tool in the toolbox and they're available for use. We just don't have them standardized at this time.
Okay. And there was a question that came in about could you discuss the ABC elements at precast plants and something, any comments about the concrete mix designs?
Well, I can tell you what the mix designs were for the three sections. Again, the next D was 6,500 psi. The Hollow-Core was 8,000 psi, and the 40-foot solid slab was 6,500 psi. And as far as the precast elements, only the superstructure, the next D's, the cord slabs, and the solid slabs are the only things that were precast and brought to the site.
Okay. It's getting on to about 9 after, and I'm going to turn it over to Jugash. We've got questions that are still coming in, so hopefully we'll get some more. Jugash?
Thank you, Paul. Paul, I think you've covered a lot of the questions that came in even during the webinar, so just a handful or less are outstanding. Now I'll begin with the first one that's asking, how did the girder deflection distribution factor for bending and shear compare with that of standard bridge beams?
I'd have to look and see how that compares with if we talk about I girders. It should be the same for moment. It should be the same distribution factor. The AASHTO located in AASHTO and LRT in the table in chapter 4, I believe it is.
Okay, thank you. Next question: would the Lawson's Fork Creek I-85 bridge replacement be considered ABC?
Quite frankly, I'm not off the top of my head. I think that was design build and I wasn't really involved in it, so I would have to look and see what the elements were of that bridge.
Okay. Next question: what volume of bridges in South Carolina are cord slabs or adjacent slab beam bridges? What percentage of these bridges are showing longitudinal cracking along the shear keys?
I don't know the percentage now. Like I said earlier, they're used very commonly on secondary roads where the traffic counts are below 3,000 vehicles per day. They're very commonly used anymore. I would have to talk to maintenance about what the percentage, see if they had a percentage on it. Anyway, as far as the reflective cracking, as far as my experience, about every bridge that I've seen that has any age on it that's a cord slab, there's usually the reflective cracking. It doesn't take too long to appear. But I don't know if there's any that don't, but everything I've ever seen does.
Okay, thank you. Next question: why did the contractor decide to use a proprietary Uhpc when they were provided the ability to use local materials to produce an Uhpc?
I'm thinking, I don't know what the contractor was thinking exactly, but I'm thinking it was probably due to risk. He had a material that he knew should be able to pass the requirements that we had for it, and instead of having to take a chance on getting somebody to mix a non-proprietary mix, and maybe it doesn't pre-qualify. So I think it was just about the risk element there.
Okay, Thank you, Terry. I think I've addressed all the questions on the list here, so I'll turn it back to Ed. Thank you so much for answering all the questions.
Thank y'all.
All right, thank you, everyone. Thanks to Terry that did a wonderful job in the presentation, and thank you to Paul and Jugish for moderating the question and answer period. Again, the registration for the upcoming conference is up right now, and so please take advantage of the early bird registration deadline. That's August 26th. And another important note is that there are limited travel scholarships that are available, and there is an application process on our website. So you can go to the site that you see on this screen and apply. These travel scholarships are only for the state and the local agency employees, and it's only for the U.S. Employees. So, and the travel scholarship includes the 4 nights of the hotel and the registration to the conference and the workshop. So we hope that you take advantage of that, and we hope to see all of you in December in Miami, Florida at Hyatt Regency. So on that note, we would like to conclude our webinar today, and so long until the next month.